Okay, so we're going to begin looking in our textbook. We're going to start in chapter 12, which deals with atoms and the periodic table. Okay, in this chapter, we're going to cover a lot of different topics. Now, I have this bulleted list here, which summarizes the major topics of the chapter. I'm not going to just sit here and read it to you because that would be boring and you can all read, but we're going to go through this list of topics step by step, and we're going to cover each one. And so let's get started. Atoms are ancient and empty. What does that mean? First of all, when we say they're ancient, we mean they're very old. In fact, the origin of most atoms goes back to the birth of the universe. That means that the atoms that make up your body, the atoms that make up everything that you use in your life, they're all literally billions of years old. When you die, you'll be cremated or buried or something like that, and the atoms that make up your body will return to the earth eventually, and they may be a part of somebody else someday. Who knows? But the individual atoms that make us all up, they're very, very old. Now, when we say that atoms are mostly empty space, remember what we think of as an atom. We have a nucleus which has protons and neutrons in it, and then around it we have electrons. And those electrons are very, very far away from the nucleus, and so what you have inside is a lot of empty space. And so when we say that atoms consist of mainly empty space, that's what we mean. Also, we can say that elements heavier than hydrogen and much of helium were produced in the interiors of stars. That means that the atoms that make up your hand and your feet and every part of you, those atoms were originally forged in the heart of a star that died billions of years ago. Some people think about this and they like to say that we are the stuff of stars because the atoms that make up our body were actually made inside of stars. Which, if you think about it, that could be pretty cool. So here's a quick check of our understanding. Which of the following are incorrect statements about the atom? Atoms have been around since the beginning of the universe. Well, that's true. Atoms are mostly empty space. That's also true. Atoms are perpetually moving. Yes, they are. Atoms are manufactured in plants and in humans during pregnancy. No, that is not true. Now, what does happen in pregnancy is a woman takes in food, and the atoms from that food are used to grow cells, including the cells of her own body and the cells of her baby. And so that's where it's not that the atoms are being created, it's that they're just being repurposed. Now, we can talk about an element. An element is a material that's made of only one kind of an atom. So, for example, gold or carbon or oxygen, magnesium, these are all examples of elements. They're pure substances. And so, if we talk about pure gold, for example, we know that gold is made up of only gold atoms. Now, if you talk about water, for example, everyone probably learned in their previous schooling that water is H2O. It's made of two hydrogen atoms combined with an oxygen atom. So the hydrogen is a pure element, the oxygen is a pure element, but when you combine two different elements, you make a compound. And so most of the things you encounter are actually compounds of different elements, but the element is the most pure unit. It's the building block. And of course, the fundamental unit of an element is the atom. This was a big question in the ancient world. So they had the idea, if I take a bar of gold and I cut it in half, I've got 2 bars of gold. And if I take one of those and I cut it in half, I've got 2 more. And so every time you cut gold, a bar of gold in half, you get smaller and smaller pieces, but everything that you have is still gold because gold is a pure element. And there was a question in the ancient world, there's come a point where you cut something in half and it's no longer gold, it's something else. And this is the basic idea of an atom. And so if I were to take a gold atom and split it apart, you wouldn't have gold anymore. So gold is the atom is the most fundamental unit of an element. It's the smallest part of an element. You can't divide the element into anything smaller than a single atom. And just generally, the term element is used when referring to macroscopic. That means in the real world kind of a thing. And we use the term atom when discussing the submicroscopic. So smaller than even a microscope can see. Okay, talking about atoms, we know that atoms are what make up all the matter around us. And up to date, there have been 115 distinct kinds of atoms discovered. 90 of those are found in nature. That means you could go out and find them in the earth somewhere, dig them up in a mine. But the rest of them, you actually have to synthesize them. You can actually manufacture these other kinds of elements in a laboratory. Most of them, however, when you make them, they're very short-lived. They exist for a while and then they change into some other kind of element through a process called decay. But the main thing that you need to remember is this key idea: an element is something that it's a material that consists of only one type of atom. Gold is an element that consists of only gold atoms. Oxygen is an element that consists of only oxygen atoms, etc. Now we know that atoms consist of protons and neutrons, which are sitting together in the nucleus, and then they're surrounded by electrons. Now, if we think about protons, you should hopefully remember, but if not, you can learn it now. Protons carry a positive charge, and they have the same amount of charge as an electron, but the electron carries a negative charge. The protons are about 1,800 times as massive as an electron, so that tells us that electrons are very tiny. And in an atom, you have the same number of protons in the nucleus as electrons surrounding the nucleus. That means that an atom typically is going to be electrically neutral. In other words, for every positive proton, you have a negative electron, and those charges will balance out. Now, it is possible for an atom to get some extra electrons sometime or to give up electrons, so they're no longer balanced. But in general, most atoms are going to be neutral, and they're going to have just as many electrons as they have protons. Now let's talk about electrons. It's an interesting fact that all electrons are identical to each other, and they repel the electrons of neighboring atoms. You might remember from your grade school science classes that like charges repel one another and opposite charges attract one another. Well, all the electrons around the outsides of the atoms are all repelling one another. And so that electrical repulsion is what prevents atomic closeness. And here you can see sort of an image of someone pressing up against a wall. Why doesn't their hand penetrate through the wall? It's because the electrons in their hand are repelling the electrons in the wall. They're pushing against one another. So that's what enables, matter to have its structure so that you can push and pull on things and the atoms don't just go willy-nilly through one another. Protons and neutrons. Now, what is it that makes something gold or makes it copper? What's the difference between gold and copper? The answer to that is the number of protons in the atom. The number of protons in an atom define what element you're talking about. And it turns out that when we list all of the elements together, there's certain patterns that repeat periodically. And so we group these atoms together in what we call the periodic table. And so we're going to see the periodic table later, but it basically lets us define what different elements we're talking about based on how many protons they have. And we call the number of protons that an element has the atomic number. So the atomic number is the number of protons in an element. Now, neutrons are particles that have the same mass as a proton, but they're electrically neutral. So protons have a positive charge, neutrons don't have any kind of charge. And since both protons and neutrons exist in the nucleus of atoms, we call them nucleons. The next concepts that we want to talk about are isotopes and atomic mass. Now, an isotope refers to atoms of the same element that contain the same number of protons but different numbers of neutrons in the nucleus. Now, remember, the number of protons in an atom is what defines that atom. It tells you what that atom is. It's either silver or it's gold. What makes it silver or gold? It's the number of protons in the atom. But if I take a particular atom of a material, that atom could have different numbers of neutrons and still have the same number of protons. So it'd be the same element, but just different versions. So one version of an element might have 20 neutrons and another version might have 22 neutrons. And it just might work out that both of those different versions are able to coexist together. Since the number of protons and electrons is the same, the amount of charge is the same, the properties don't really change very much when you have different isotopes. And so very often different isotopes of an element have similar characteristics. Now, in the previous slide, we talked about atomic number. That's the number of protons that an element has, and it defines that element. Then we have atomic mass number. The atomic mass number is the total number of protons plus the total number of neutrons. And so we have the atomic number, which is just protons, and we have the atomic mass number, which is protons plus neutrons. And so if you subtract the atomic number, which is the number of protons, from the mass number, which is the number of protons plus neutrons, what you'll end up with is the total number of neutrons. Okay. Now, just to recap, the atomic mass is the total mass of the atoms, the protons and the neutrons. Technically also the electrons, but remember the electrons are really, really tiny, so they don't affect it very much. And when we look at the periodic table later on, we'll talk about the atomic mass, and we'll see that it's listed in terms of a unit called atomic mass units. And one atomic mass unit is equal to 1.661 times 10 to the minus 24 grams, or times 10 to the minus 27 kilograms. So it's a very, very tiny unit of mass, but that is what we'll see on the periodic table later. Okay, let's check our understanding with this little quiz. The atomic number of an element matches the number of, what do you guys think? Is it the number of protons in the nucleus of an atom? It is. That's what the atomic number is. So is the answer A? Well, let's check and keep going. Is it the number of electrons in a neutral atom? That means there are as many electrons as there are protons. That's what you have in a neutral atom. So B is correct also. That means C is correct because both of the above, A and B, are correct. D is not correct, so the correct answer is, dun dun dun, C. Both of the above. Okay, let's check our understanding with another example. A nucleus has an atomic number of 44 and a mass number of 100. How many neutrons does it have? Now, I want you guys to pause the video and try to work this out yourself. So we have 44 is the atomic number, 100 is the mass number. How many neutrons does the atom have? Stop, seriously, pause the video, sit down, and work through it. It'll only take you a minute. See if you can figure it out. Did you pause the video? Are you pausing? Are you working it? All right, I'm going to hope that everybody did that now. So let's see how to do this. Now, the atomic number is 44. That's how many protons there are. 100 is the number of protons plus neutrons. That's the mass number. So 100 protons plus neutrons minus 44 protons, that leaves 56 neutrons. And if I look over here, I see that's option B. So our answer is B, 56. The next thing that we're going to talk about is the so-called periodic table. Now, you may have seen this before. It's a way of organizing all the different possible elements that there are, both the ones that are found in nature and the ones that are manufactured. I want to make sure that you understand the periodic table is not something to be memorized. Instead, we learn how to read it and interpret the information that's stored there. A chemist will use the periodic table much like a writer would use a dictionary. So if you need to know something about helium, you can go look up helium on the periodic table and you can find out different things about helium. And so what my goal is for you guys is to be able to understand how the periodic table is organized and the different kinds of information that you can glean from it. In this slide, we can see a example of a periodic table, and we can see some of the different elements are highlighted. For example, you can see the element with atomic number 47 is Ag, and that's actually the chemical symbol for silver. Now, Ag, why wouldn't they call it Si? Because some of these names for different chemical elements were originally made in Latin. The Latin word for silver is argenti, and so Ag comes from Latin, and that's the symbol for silver. And so silver, we can see, has an atomic number of 47. That tells me that silver has 47 protons. And so anyway, you can see some different elements are highlighted. Here's carbon, silicon, helium up here, some others. You can, if you want, pause this slide and read through some of these different elements, titanium and silicon and mercury and others. But it's the part here in the bottom middle that really concerns us. This is the periodic table of the elements. Now, one thing that's a little bit weird about the periodic table is you can see there's this kind of, purple color here. It's sort of wedged in here. And so you can imagine that this block down at the bottom gets kind of wedged in right in between these two here. And we'll talk about why that is in a minute. But we want to go ahead onto some of the next slides where we'll talk about the periodic table and some of its features in more detail. So the first thing you should know is that the periodic table is a specific way of organizing all the different elements that exist. And as you saw, there were different columns and rows of elements layered together, and the vertical columns are called a group, and the horizontal rows are called a period. I'll illustrate that on the next slide. So what we said in the previous slide was that the vertical columns represent a group. So for example, take this group here over on the rightmost column. So we have helium, neon, argon, krypton, xenon, and so on. All of these different elements belong to a group called the noble gases. And each of these different elements have similar properties. And so elements with very similar properties are connected together in different groups. Now, in addition to this structure, vertical columns having the same properties. So if we come over here to the leftmost column, all of the elements in this column have similar chemical properties. If I pick this column, these elements have similar chemical properties. And again, those vertical columns, they're called groups. Now, the rows, the horizontal rows, they're called periods. And so the first period only contains hydrogen and helium. The second period contains lithium and beryllium, and then the rest of these elements over there is boron and carbon and nitrogen and the others, oxygen, etc. As we continue to go down, we see eventually you get this whole row is filled in, this whole row is filled in. And what causes these rows to be formed this way is that each row, when you go on to the next row, certain trends repeat. And so there's a periodicity to the way that these elements behave. That's why it's called the periodic table, because we go from here to here, and all of these elements along this row follow certain types of chemical trends. And then when you start over on the next row, they follow the same types of trends. And so that's why it's the periodic table. So we have all of the elements grouped together in groups, which define similar properties, and periods, which describe trends as you move from one element to the next. And again, you can look at the numbers. The numbers at the top are the atomic numbers, and so each of these numbers tell us the number of protons. That is, the number of protons contained in that particular element. Now here we see a depiction of part of the periodic table, which is highlighting some of the different periods. So you can see the first period is hydrogen and helium, the second period, the third period, the fourth period. And what you can see is one of the trends that's very clear is that as you go from left to right, the size of the element gets smaller. In other words, the size of the atoms of the element gets smaller and smaller. That's what these spheres are depicting. And so if I look at this sphere here, this is sodium. Its atoms are much bigger than, say, that sphere, which would be argon. And that's one of the patterns that you see in the periodic table. So the atoms on the left start out big, they get smaller and smaller and smaller, and then as you continue going up in atomic number, suddenly you jump and you've got another really big atom. And so this periodically repeats over and over and over again, this kind of a pattern. And so that's why it's called the periodic table. Now, of course, you can look, say, for example, here, this atom and that atom. This one's a little bit bigger than the one before it, but the trend is still clear that you're going from a bigger atom to a smaller atom as you go from left to right. So different groups have different names, and so the leftmost group 1 is called the alkali metals, and group 2 is called the alkaline earth metals. The group in the middle is considered to be what are called transition metals. And a lot of the things that people normally think of as metal, like lead and gold and silver, those are in the transition metal category. There's a bunch of atoms over here. They don't really have any common name, but over here you see, for example, the halogens and the noble gases, which I mentioned previously. And so some of these different groupings of atoms, they have similar chemical properties, and they get classified into these different group names. Now here you see a full-on picture of the periodic table, and I have included a copy of this PowerPoint in your Canvas shell, so you can actually print this slide out from your PowerPoint and you have a periodic table that you can use for some of your homework. So we can look now at sort of a check your answer kind of a situation. Which is larger, a lithium atom or a fluorine atom? Well, remember, the trend is to go from a bigger atom to a smaller atom. So we would expect the answer to be lithium. So the answer is that lithium atoms are bigger than fluorine atoms. Here we see another example. Which is larger, an arsenic atom or a sulfur atom? Again, we know. Actually, before I tell you, what do you think? Which is bigger, an arsenic atom, a sulfur atom, or maybe you just can't tell? Well, they're not in the same period, but they are in different groups. And we know that as you go along a period from one group to another, that the atoms tend to get smaller as you go from left to right. So we would expect arsenic to be bigger than sulfur. And actually, that turns out to be the case. The answer as to which one is larger is arsenic. And then finally, for this video, we want to talk about the difference between physical models and conceptual models. A physical model represents an object at a convenient scale. So imagine you wanted to make a scale of the solar system. You might, for example, start with a large beach ball and say that's going to be the sun, and then you might have something like a tennis ball and say that's going to be the earth. And then you might have something like a ping pong ball and say that's going to be the moon. Now, that might not be an exact scale, but it would be something to maybe give you an idea about different sizes. And so the point isn't whether or not those would be good choices for that model. The point is that what you have is some physical objects representing something that you can look at, touch, feel, etc. That's a physical model, and it replicates what you're studying at some more convenient scale. So if something's really, really tiny, you might make your model be bigger. If something's really, really big, you might make your model be smaller, but you want it to be something that you can sort of deal with hands-on. Now, a conceptual model is simply a way of thinking about something. And it could be a computer simulation, it could be an equation, it could be any number of ways of representing a system in a conceptual way. That is, you're not actually building something to represent the model, you're just finding ways to think about it. And it says here on our slide that an atom is best described by a conceptual model. Well, yes and no. There are ways of making physical models of the atom, and that can be a good way of understanding its constituent parts. But when you really want to understand how the atom works, then you really need to rely on conceptual models. And that's why they tend to be preferred. In any case, we have come to the end of this presentation, but we will have another one on this chapter, on this material, and you guys can go through these, take your notes, and then you'll be able to take your quizzes in Canvas. You'll be able to do your homework. Now remember, these PowerPoints and these video presentations, these are supplements to what's in your textbook. You really need to read the chapter to get the full details of what I've been talking about. So please do read the chapter because you'll need that for the quizzes and for the homework. So good luck, and I'll see you in the next video.